lot later. Now, imagine we have a string of a certain length L. It is fixed at both ends. And if I disturb the string, I'm going to cause a wave traveling to the left and to the right, and when they hit the wall, they bounce back. So eventually you're going to have two waves, one traveling to the right, another traveling to the left, and they're going to interfere with each other to form a standing wave. So eventually you're going to get these loops. Okay, here's the thing. L is fixed, L cannot change. How many loops can you contain between here and there? Okay, the idea is you have to look at what happens at the border, at the boundary, left border and right border. Make sure that you understand that this end is a node, so is that end. Why? Because remember, the string is held fixed at this point and at that point. So there can be no oscillation whatsoever at this point and that point. So this must be the beginning of a loop, and over there must be the end of a loop. So what I draw here is one possibility. Okay, beginning of a loop, another one, another one. How many loops do I have in this drawing? 3 loops. Now, do I have to have 3 loops? No, I can have as few as only 1 loop. Okay, so it's just a giant loop like this. I can have 2 loops. Of course, I can have 3 loops. I can have 4 loops. I can have a whole bunch of loops. I can have very small loops like this, in principle. I squeeze in a whole bunch of them. Okay, but can I have, say, 1.5 loop? Let's look at what 1.5 loop means. Okay, 1.5 loop means you start with a loop, right? You start with a loop, like this, but you follow this by half a loop, like this. You end with half a loop. What is wrong with this picture? Nothing is wrong here because this end is held fixed. But what about that end? That end happens to be an untimed node. What that means is that at that end the string is not held fixed, rather it oscillates, and here's the amplitude of, actually twice the amplitude of oscillation. That, of course, is not allowed because you know the other end is also fixed. So you see, you can have 1, 2, 3, or no matter how many no loops you have, you can squeeze them in between. What you cannot have is a non-integer number of loops. Okay, in other words, the number of loops that you can fit in between 2 fixed ends of a string must be equal to an integer. Okay, so L must be n loops. Here n is an integer. Actually, it's a natural number, 1, 2, 3, so on. But you know, each loop is half a wavelength long. We know that, right? So L equals to n lambda over 2. That tells you that the wavelength lambda that can exist on this string cannot be just anything. It must satisfy this formula. Okay, there is not a unique value, of course, because this n can change, but n is not just any number. It has to be a natural number, 1, 2, 3, 4, whatever. So you can only have a series, a discrete series of lambda values that can possibly satisfy this formula. Here is the longest possible such wavelengths. Here is the second longest, third longest, and so on, because as the loops shrink, so do the wavelengths. Okay, in mathematics, in physics, we give it a name. This longest possible loop corresponds to the lowest frequency, or the longest wavelengths. We give it a name. We call it fundamental mode. Okay, so that is not allowed. It is otherwise known as first harmonic. Here, the term harmonic, just like in oscillation, harmonic here means frequency. So this is the first or lowest allowed frequency that can oscillate on the string. The next one, this is the second longest possible wavelengths. It's only got 2 loops, and it has the second lowest frequency. Correspondingly, we give it a name. We call it second harmonic. Okay, this will be the nth harmonic. What's n? That depends on how many loops you have. Okay, first harmonic for one loop, second harmonic for two loops. You count 1, 2, 3, 4, 5, 6, 7, 8. So that's the 8th harmonic, the one I'm drawing here, okay? 8th harmonic. All these harmonics are possible. That will give you the allowed wavelengths or allowed frequencies. Okay, so depending on the length of this string, you have fixed the possible wavelengths. Lambda 1, here's lambda 1, lambda 2, and so on. Here's lambda 8, and so on. And of course, you can also change the physical conditions of this string to fix the wave speed on that string. Remember, the speed of the wave on the string is the square root of tension over mu. Okay, by fixing tension and fixing mu, you can also fix the speed. Lambda is already fixed. Lambda depends only on the length L. Okay, only on the length L. Then you also fix the wave speed. That tells us what kind of frequency we can possibly get. In other words, the frequency that can exist, or the frequencies that can exist on that string with both ends fixed, are not just any value. They must satisfy certain conditions. That is how we can select frequencies using this string. Okay. I have here some more drawings. As you can see here, we start with a flat string of length L with both ends fixed. This is the longest possible wavelengths with only half a loop fixed, sandwiched in between here and there. The frequency is the lowest because the wavelength is longest. That's F1, the so-called fundamental mode. And what's the length L? It equals only one loop, which is half a wavelength. That wavelength is the longest one. We call it lambda 1. N equals 1. N is the number of loops. Okay, so N equals 1. It also tells you this is the nth harmonic. So this would be the first harmonic because N equals 1. Here N equal to 2. You have 2 loops. That's the second harmonic. The frequency is the second lowest, and the wavelength is the second longest. Here is N equal to 3. That's what's called, of course, third harmonic. The same length L now has to contain 3 loops. So L equals 3 times half a wavelength. Okay, this is a depiction of the first, second, and third harmonic. Of course, you can have more harmonics after that. So you get the idea. Now, I'm going to derive something interesting. And it's called piano maker's formula. There is a lot of physics going on in musical instruments. In particular, when you play piano, when you strike a certain key, you know there's a certain distinctive frequency coming out, right? How is that frequency determined? When you design a piano, when you make a piano, you want to make sure that the key is designed such that when you strike that particular key, a certain frequency is heard. Okay, what determines that frequency? Well, that's the so-called piano maker's formula. Here is a top view of a grand piano made of all these keys. Okay, a top view. You know, grand piano is always designed such that the left end is longer and the right end is shorter. Why is that? Well, because if you open up the cover of the grand piano, what you see in the back, you see a whole bunch of strings, okay? A whole bunch of strings. And over here you have shorter strings. Over here you have longer strings. Why longer strings? Because what we want to play is, we want lower frequency keys here, higher pitches or high frequency keys over there. Why is it that lower frequency requires a longer string? Well, let's look at the formula. Let's say between here and there, let's look at a particular string. Its length is L, okay? L equals N times lambda over 2. That is the formula that determines what kind of wavelengths can exist, right? Okay, the wavelengths is not what we're interested in. We're interested in the frequency produced, right? Because we hear frequency, we don't hear wavelengths directly. So let's look at the frequency. All right, N over 2. The wavelengths equals to the speed of the wave divided by the frequency. Okay, so we're interested in the frequency. Let us now solve for the frequency, shall we? Okay, let's solve for the frequency. So the frequency equals to N times V over 2L. is an integer, 1, 2, 3, 4, whatever. L is the length of the string. What about V? Well, V is the speed of the wave on that string. And that's determined by the tension and linear mass density. So let me write this down here. N over 2L, square root of F over mu. Okay, that is the speed of the wave on the string as we learned in chapter 16. Now I can write this down as N times F1. What's F1? F1 is the value for F when N equals 1. As a matter of fact, let me use a subscript N here because this indicates there are a series of frequencies, F1, F2, F3, F4, that can be heard as the string vibrates. Here's a string of length L with tension F as linear mass density mu. So Fn is equals N times F1. Okay, this formula is called the piano maker's formula because it tells us how to design a piano string such that it can produce these frequencies F1, F2, F3, F4, and so on. You notice not a single frequency is produced, rather a series of frequencies. But what's most important is F1, the fundamental frequency. That's what determines what kind of note is it. Is it an A note or C note, whatever. That's determined by the very first one. Of course, if you know the first one, F1, and F2 is simply 2F1, and F3 is simply 3F1, and so on. All these are also determined. Okay, you can understand why the longest strings have been placed on the left side of the piano because the left-hand side of the piano, when you strike a key, you produce a low frequency sound, right? Low frequency. So F is low. How do you make F low? You want to make L large, okay? You want to make L large. So that's why you have longer strings. Over here, you have higher frequency or higher pitch, which requires a shorter wavelength, shorter length of the string for higher frequency. So that's how it works. Now, our piano maker not only changes the length of the string, he can also change mu. In other words, what kind of material is being used for these strings. If you open up the case of a grand piano, you will see that the strings on that side are not only longer, but they also appear to be thicker. That makes sense because you don't just want a large L, you also want a greater value of mu to further reduce the frequency. Okay, this is particularly important if you don't want to make a large piano, if you want to just make a compact size piano. So this side is not terribly long. Okay, so L is limited because that's limited by the size of the piano case, right? So you don't have a very large L, yet you want a very low F. How do you achieve that? Well, one thing you can do is you can use heavier strings with greater value of mu. That's how we adjust it. Okay, now L is fixed once the piano string is already in place. Mu is also fixed because, that's for a particular string, mu is never going to change. Okay, so if you play this particular key, you find the frequency is not right. How does one possibly adjust that? Okay, how does one, in other words, tune the piano? Well, look, you cannot change L or mu unless you change the string itself. So what do? Well, the only variable that you can adjust is F, right? That is the tension on the string. And that is how the piano tuner comes in to adjust the frequency for you. Okay, the piano tuner deals with the tension on the string. He uses a plier to either loosen or tighten the string. If you loosen the string, then of course you're reducing the tension, therefore reducing the frequency, softening the pitch. And if you tighten it, of course F is greater, the tension is greater, and the frequency will go up. So that is how a piano tuner works, basically by adjusting the tension on the string. So that's the piano maker's formula, and the piano is just one of many common musical instruments. In fact, each musical instrument, whether primitive or sophisticated, they all consist of applications of the principles of physics. In particular, two things. One is you must know how to select a certain frequency. Otherwise, you cannot play a certain tune. Okay. And secondly, you must learn how to amplify that sound so that the music can be heard by a large audience. So those are the two things that goes to design of any musical instrument, and we're going to look into it. Okay. So let's take a brief look at what's called physics of musical instruments. Okay, in an orchestra, you have two large classes of instruments. There are string instruments, there are wind instruments. String instruments, for example, piano, of course, is a string instrument. You also have violins, violin, viola, double bass, cello, all these are string instruments. Then you have wind instruments, okay, like pipes, clarinet, oboe, those things. They are different, but they each, like we said before, must fulfill these two goals, and that is you first have a way of selecting the frequency, and secondly, must amplify the sound. Okay, we're going to talk about amplification of sound a little later, but how does each instrument select a certain frequency to play? So how do you adjust the frequency when you play it? Well, with piano, that's not a problem because each key, when you strike each key, the key in turn strikes a certain string, and from the piano maker's formula, each string produces a distinctive series of frequencies depending on its length, on the tension, and linear mass density, right? But what about a violin? You know, violin has only several strings. It doesn't have one dedicated string for each note, right? So how do you possibly use only several strings to produce all these possible frequencies? How do you do that? Okay, here is the trick, and that is so-called fingering. Now you notice from the piano maker's formula, even though the violin is not a piano, the idea is the same as far as the physics is concerned. You go back to the piano maker's formula. Okay, you want to produce a certain frequency, right? In which you want a certain value of F1, so that you know this is an A note, not a C note, whatever. You cannot change mu because that is fixed by the nature of the string. What about F? Well, you can change it to some extent. Okay, you can put your finger on it. You can sort of increase the tension a little bit, but it's limited. So what else can you change? Well, the trick here is to change L. Now, how do you change the lengths? Well, this is what's called fingering. Everybody who has played violin or has seen people playing violin, you know what I'm talking about. You put a finger at a certain portion of the string, and that pretty much stops that part of the string from oscillating. You have effectively shortened the string, the length of the string, to from one end of the string to where that finger is placed. So you are changing L by tapping the finger at a particular location on the string. Therefore, you can change the frequency. So this is how you play the violin, use the violin to produce different tunes, different frequencies, is by placing your finger at a certain location by therefore changing L. Okay, now what about wind instruments, flutes and pipes, and oboe, clarinet, that sort of thing? Okay, how do they select frequencies? Well, they don't have a string, do they? Rather, they have air. Okay, they don't have a string, they have just a chamber of air, or column of air, like a flute, for example. Okay, so how do they select frequency? This is what we're going to discuss next. That is, we're going to look at the resonance condition of a vibrating air column.